201 million years ago, the biosphere of Earth faced a radical thermodynamic reset. The boundary between the Triassic and Jurassic periods was not marked by a slow, gradual transition, but by a massive, violent geological trauma. Colossal fissure eruptions tore across the supercontinent of Pangaea, releasing unimaginably vast volumes of carbon dioxide and sulfur dioxide directly into the atmosphere. This sudden, overwhelming injection of greenhouse gases triggered severe global warming and the rapid acidification of the global ocean. Within a very short geological timeframe, more than half of all known species completely vanished from the fossil record. The dominant terrestrial animals of the Triassic, an extensive and highly successful lineage of crocodile relatives, known as the pseudoseuchians, collapsed almost entirely. Their sudden eradication left behind a vast, empty ecological landscape. But this profound void in the food web did not signify the end of complex life. Instead, it presented an unprecedented opportunity for a previously marginal group of fast-moving reptiles that had spent the last 30 million years surviving in the evolutionary shadows. We call them dinosaurs. The biological hardware of these early dinosaurs, tested and ruthlessly refined during the harsh, arid climatic extremes of the Triassic, suddenly found itself operating without significant ecological competition. At a planetary scale, this massive extinction event functioned as a severe evolutionary bottleneck, violently sweeping away the old terrestrial order and clearing the entire stage for a new biological empire. A planetary biosphere's capacity to survive its own internal thermodynamic resets is a universal test of resilience. The advanced physiological mechanisms that allowed dinosaurs to cross this deep time boundary would soon drive them to aggressively expand across the fracturing continents, ultimately evolving into the largest, most thermodynamically extreme terrestrial machines the planet has ever sustained. Today we will explore the Jurassic Period explained, how dinosaurs rose to rule the Earth. Please like and subscribe and leave a comment below letting us know exactly where and when you are watching this documentary. The physical structure of the world the first dinosaurs inhabited was fundamentally unstable. For tens of millions of years, nearly all the landmass on Earth had been locked together in a single, colossal supercontinent known as Pangaea. But a landmass of this magnitude is not merely a geographic feature. In the realm of geophysics, it operates as a massive thermodynamic barrier. Continental crust is composed primarily of relatively low-density granitic rock, which acts as a highly effective thermal insulator. Deep beneath this crust, the planetary engine of Earth continued to operate without pause. The decay of radioactive isotopes within the core and the lower mantle generated immense, unrelenting heat. Normally, much of this thermal energy escapes through the ocean floor, where the oceanic crust is thin, highly conductive, and constantly recycling. But beneath the vast, unbroken expanse of Pangaea, the heat had absolutely nowhere to go. Over millions of years, thermal energy pooled beneath the supercontinent. The solid but highly pressurized rock of the deep mantle began to upwell, creating a gargantuan mantle plume. This is a universal mechanic of planetary physics. Any rocky body with an active core and a stagnant outer shell will eventually build up enough internal pressure to fracture its own surface. As the heat accumulated, the lithosphere beneath Pangaea began to warp, dome upward, and stretch to its absolute physical limits. The tension reached a critical threshold roughly 201 million years ago. The continental crust did not simply crack under the strain, it was violently ripped apart. The supercontinent fractured along a massive central seam, initiating the division of the world into two distinct landmasses, Laurasia to the north and Gondwana to the south. This rupture would eventually widen over millions of years to become the Atlantic Ocean. But the immediate consequence of this tectonic tearing was the birth of the Central Atlantic Magmatic Province. This was not a localized volcanic chain or a series of isolated mountain peaks. It was a planetary-scale fissure system, a terrifying network of tectonic lacerations extending for thousands of miles across what is now North America, Europe, South America, and Africa. Decompression melting of the upwelling mantle produced unimaginable volumes of liquid rock. Over a remarkably brief geological window, millions of cubic miles of molten basalt violently flooded the surface. To grasp the sheer scale of this event, one must visualize the tide of heavy, dark lava completely burying an area larger than the modern continental United States, stacking up in sequences hundreds of feet thick. The physical mass of this eruptive material was so great that it locally depressed the continental crust, permanently altering the topography of the planet. But the most lethal weapon unleashed by the Central Atlantic Magmatic Province was not the magma itself. It was the invisible payload of volcanic gases. As the magma forced its way upward through the continental crust, it did not travel through empty space. It incinerated vast, ancient subterranean deposits of limestone, salt, and organic-rich coal. This interaction effectively weaponized the crust of the Earth. It functioned as a gargantuan, uncontrolled chemical refinery, violently liberating trapped volatiles into the atmosphere through a process known as contact metamorphism. The primary outputs of this planetary exhaust system were sulfur dioxide and carbon dioxide. This atmospheric injection fundamentally altered the chemical equilibrium of the world. Initially, the massive clouds of sulfur dioxide aerosols dominated the upper atmosphere. These microscopic particles are highly reflective, functioning like a planetary mirror that bounced incoming solar radiation directly back into deep space. This triggered sharp, severe volcanic winters, plunging the planet into sudden, freezing darkness. The dominant cold-blooded reptiles of the Triassic era, highly dependent on ambient solar energy to move, hunt, and digest, found themselves rapidly paralyzed by the dropping temperatures. But the problem did not stop there, and the true catastrophe was a matter of atmospheric pacing. The sulfur dioxide eventually washed out of the atmosphere as highly corrosive acid rain, devastating terrestrial plant life and acidifying shallow freshwater systems. Once the sulfur cleared the skies, the long-term consequence of the eruption took absolute control. The colossal volumes of carbon dioxide remained trapped in the atmosphere. Carbon dioxide is a highly efficient greenhouse gas. It is entirely transparent to incoming visible light from the sun, but highly opaque to the thermal infrared radiation trying to escape back into space. With atmospheric carbon dioxide concentrations spiking to levels nearly 4 to 5 times higher than those of the pre-industrial modern era, a runaway greenhouse effect gripped the planet. Global temperatures rebounded from the volcanic winter and skyrocketed. This extreme thermal whiplash, transitioning rapidly from sudden freezing dark to suffocating heat, was the primary kill mechanism of the extinction event. The oceans, acting as the ultimate planetary heat and chemical sink, absorbed billions of tons of the excess carbon dioxide. This chemical reaction flooded the water with hydrogen ions, robbing the ocean of carbonate. Marine organisms that relied on calcium carbonate to build their shells and skeletons literally began to dissolve while still alive. The marine food web collapsed entirely from the bottom up. At a planetary scale, the meaning of this extreme climatic swing changes completely. It provides a stark, terrifying look into the fragility of biospheres. In the modern fields of astrobiology and the search for extraterrestrial intelligence, scientists closely model these exact types of sudden carbon injections. A planetary biosphere's capacity to survive its own internal thermodynamic resets might be a universal bottleneck, a great filter that determines whether complex life can persist long enough to develop advanced intelligence. A rapid outgassing event that overwhelms a planet's natural carbon sinks can permanently strip away habitability, transitioning a living world into a dead, pressurized greenhouse similar to modern Venus. Earth narrowly avoided this permanent sterilization. The physical tearing of Pangaea engineered a completely new, hostile world. The air was thick, heavily acidic, and trapped heat with brutal efficiency. The global systems that had stabilized the previous period were fundamentally broken. The massive, slow-moving animals that had ruled the Triassic could not adapt their metabolisms or their heavy bodies to a world that was suddenly baking. They perished in the heat and the shifting landscapes. Yet this absolute ecological devastation was exactly what the early dinosaurs required. The atmospheric crisis created the precise evolutionary pressure cooker needed to forge the biological dominance of the animals that would rule the deep time of the Jurassic. The supercontinent of Pangaea was not just a vast expanse of inert geography. It was an extreme thermodynamic engine that strictly governed the atmosphere of the Earth during the Triassic period. Due to its colossal physical size, the interior of the landmass experienced brutal thermal fluctuations. The thermal inertia of solid continental rock is fundamentally different from that of liquid water. During the summer, the immense stretch of the continental interior absorbed solar radiation and heated at an alarming rate, creating a profound, massive, low-pressure sink over the center of the landmass. In contrast, the universal ocean, Pangaea, maintained a much cooler, stable temperature, generating massive zones of high pressure. The unyielding laws of thermodynamics dictate that fluids must move from high pressure to low pressure. This gradient triggered massive, violent winds loaded with oceanic moisture surging toward the land, a planetary weather system known as the mega monsoon. However, topographic friction and immense inland distances ensured that this torrential precipitation discharged almost exclusively on narrow coastal margins. The storm clouds were completely stripped of moisture long before reaching the continental heart. Observational data extracted from the stratigraphic record confirms this climatic violence. Geologists identify the Triassic core through thick layers of evaporites, minerals crystallized by the extreme evaporation of ephemeral lakes, and vast Aeolian dune sandstones that prove an almost total absence of deep moisture. It was an environment of relentless hyper-aridity, a global desert where biological survival operated on the absolute extreme margins of heat tolerance and dehydration. But as the tectonic faults of the Central Atlantic magmatic province shattered the continental architecture, the physics of the planetary atmosphere was completely rewritten. The tectonic plates separated, and the waters of the Tethys Sea and the nascent Atlantic Ocean violently spilled into these new subsidence trenches. Meteorologically, the introduction of shallow seas directly into the fractured heart of the supercontinent acted as a vast, highly efficient liquid cooling system. The intrusion of water disrupted the formation of the hyperheated terrestrial core. Without that extreme temperature differential between the center of the landmass and the surrounding ocean, the colossal circulation cell of the mega monsoon simply collapsed. The global climate transformed radically. It shifted from a violent, binary system of scorching deserts and stormy coasts to a highly distributed, warm, and uniformly humid meteorological environment. Global temperatures stabilized. The thermal gradient between the equatorial tropics and the high latitudes flattened dramatically. and polar ice ceased to exist on the planet. At a planetary scale, the significance of this geological shift completely alters our understanding of biological stability. In modern disciplines like astrobiology and the search for extraterrestrial intelligence, the distribution of surface water through continental seas is considered a critical metric and a predictive model for long-term habitability. A rocky world trapped in a phase of unbroken supercontinents tends to be deeply hostile, restricting advanced biospheres to narrow, fragile, habitable corridors along the coasts. Tectonic fragmentation, therefore, is not merely a geographic event. It is a planetary moisture distribution mechanism that stabilizes the climate. This is a fundamental prerequisite for complex ecosystems to sustain themselves and expand against stellar and geological perturbations over deep time. With the collapse of the desert and the arrival of a global moisture regime, the surface of the Earth became a receptive canvas for an unprecedented biological revolution. And the atmosphere provided the perfect chemical engine. Loaded with the carbon dioxide injected by the volcanic eruptions of the extinction event, the air acted as an immense gaseous fertilizer. The levels of carbon dioxide in the early Jurassic atmosphere were staggering, reaching concentrations that exceeded 4 to 5 times the levels observed in the modern pre-industrial era. In this vast, humid greenhouse, saturated with carbon, naked seed plants, scientifically grouped as gymnosperms, experienced an explosive evolutionary expansion that redefined the biomass of the planet. Vast lineages of primitive conifers, cycads, and ginkgos marched into the continental interiors, rapidly colonizing what were previously wastelands of sand. At a cellular anatomical level, the absolute excess of carbon dioxide allowed these plants to radically optimize their water efficiency. Stomata, the microscopic pores located on the surface of leaves, used for vital gas exchange, did not need to open as widely or remain exposed for as long to capture the carbon indispensable for photosynthesis. This dynamically reduced the passive loss of pure water through transpiration, allowing gymnosperms to colonize and dominate microclimates, altitudes, and latitudes that would have been biologically prohibitive in any previous era. But the problem does not stop there, and this leads to a much deeper feedback system. This overwhelming expansion of biomass was not merely a passive response to a favorable climate. It rapidly became the primary active climate regulation mechanism of the Earth. By extracting trillions of tons of carbon dioxide from the air to synthesize and build vast forests of woody trunks and dense foliage, the gymnosperms functioned as planetary-scale biological carbon sink pumps. They slowly began to mitigate the runaway greenhouse effect that threatened to permanently sterilize the planet following the magma fractures. And it is precisely here that the botany of the Jurassic connects directly with cosmic questions regarding the longevity of civilizations. The capacity of a biosphere to act as a robust chemical buffer determines the actual lifespan of a biological system. When a planet suffers a massive thermal perturbation from an injection of greenhouse gases, if life does not respond by rapidly sequestering that carbon into solid biomass or geological strata, the world crosses a critical threshold. It faces the imminent risk of an unrecoverable runaway greenhouse effect. The atmospheric great filter that theoretically silences countless terrestrial worlds in the galaxy, transforming them into spheres of suffocating pressure similar to modern Venus. The dense, silent gymnosperm forests of the Jurassic did not just serve as an ecological backdrop, they literally stabilized the thermostat of the Earth, preventing the total thermal collapse of the system. However, this botanical victory introduced a fascinating evolutionary trap for the animal kingdom. The molecular architecture of gymnosperms was heavily based on the production of extreme structural and defensive compounds, such as lignin and highly crystalline cellulose. Furthermore, the leaves and fronds of these plants were heavily armored with thick wax coatings and impregnated with secondary resins and chemical toxins. This immense reserve of photosynthetic energy was deliberately engineered to resist biological degradation and actively deter consumption. This leads to an inevitable anatomical consequence. If the entire planet is suddenly covered by an ocean of food that is simultaneously toxic and structurally impenetrable, herbivorous life faces an extreme crisis of adaptation. To extract effective calories from this chemically locked energy source, vertebrates could not rely on simple digestive systems. They required internal processing equipment of an industrial scale. Repeated chewing was entirely insufficient. The plant molecules had to be slowly dismantled through symbiotic fermentation, using specialized bacterial biomes within the gut itself. But the thermodynamics of bacterial fermentation of fibrous material is inescapably slow. It demands that an enormous volume of plant matter be retained at high constant internal temperatures for uninterrupted days or weeks. If this metabolic law is true, it not only explains the dietary ecology of a bygone era, but it dictates the fundamental rules of animal size and evolutionary design. To house a retention and fermentation chamber gigantic enough to process the daily rations necessary to keep the organism alive, the host animal must, obligatorily, possess colossal body mass and volume. The defensive botanical chemistry of the gymnosperms silently but inexorably constructed the exact metabolic imperative that would force the future herbivorous dinosaurs to shatter the barriers of conventional size and transform into the absolute biomechanical titans of prehistory. For over a century, the scientific consensus trapped dinosaurs in a fundamentally flawed biological paradigm. Because they were classified taxonomically as reptiles, early paleontologists assumed they operated entirely on ectothermy, meaning they relied strictly on external environmental heat from the sun to regulate their core body temperature. Under this classical model, dinosaurs were visualized as sluggish, slow-growing, solar-powered machines, heavily constrained by the ambient temperature of their immediate environment. However, this ectothermic model completely collapsed when confronted with the physical reality of the Jurassic Period. A cold-blooded metabolism simply cannot generate the sustained biomechanical power required to support the massive anatomical frameworks of the apex predators, nor could it explain the explosive growth rates necessary for the giant herbivores to survive to adulthood. To resolve this profound thermodynamic paradox, modern science had to stop looking at the macroscopic shape of the fossilized skeletons and start examining the microscopic architecture of the bone itself. This is the science of paleohistology. Bone is not inert structural scaffolding. It is a highly active, living tissue that meticulously records the metabolic history of an organism throughout its life cycle. By extracting thin cross-sections of fossilized femurs and tibias and analyzing them under polarized light microscopes, researchers can read the biological timeline of a dinosaur exactly like a climatologist reads the growth rings of an ancient tree or an ice core. What the microscopic data revealed shattered the reptilian model forever. In modern cold-blooded reptiles like crocodiles or monitor lizards, bone growth is slow, highly dependent on seasonal temperatures, and heavily marked by dense, closely packed rings known as lines of arrested growth. These lines indicate periods where the animal effectively shut down its metabolism during cold or dry seasons. But when scientists observed the cellular matrix of Jurassic dinosaurs, they found vast regions of what is known as fibrolamellar bone. This is a chaotic, rapidly deposited, highly vascularized type of bone tissue, woven with a dense network of blood vessels and osteons. It is the unmistakable histological signature of aggressive, continuous biological deposition. To lay down bone tissue at such an extreme velocity the animal must possess a massive, relentless internal furnace. It requires an endothermic metabolism, universally known as warm-bloodedness. This discovery created a direct conceptual bridge to their anatomy. The unidirectional respiratory system, with its complex air sacs, which we explored previously, was not just a weight-saving measure. It was the absolute thermodynamic prerequisite to supply the immense volumes of oxygen needed to fuel this raging internal fire. But biology rarely deals in binary absolutes, and the histological data introduced a new layer of scientific debate. While small predatory theropods showed clear signs of total endothermy, heavily resembling modern birds, some of the larger dinosaurs presented a physiological puzzle. Their bones displayed the rapid, vascularized growth of mammals during their juvenile stages, but as they reached adulthood, they still retained distinct seasonal lines of arrested growth. This suggested their metabolisms could fluctuate in ways modern mammals do not. This friction in the data birthed the hypothesis of mesothermy, an evolutionary middle ground. Under this model, dinosaurs generated vast amounts of internal metabolic heat to fuel rapid growth, but they did not strictly defend a single unwavering core temperature. They allowed their internal thermostats to drift slightly with the seasons, saving massive amounts of caloric energy during lean periods, while still fundamentally outperforming any true cold-blooded competitor. For the colossal sauropods, the physics of thermodynamics shifted yet again, creating a phenomenon known as inertial homeothermy, or gigantothermy. When an animal reaches a certain extreme volume, the laws of physics dictate that its body simply cannot lose heat fast enough to cool down overnight. Their sheer physical mass became an evolutionary adaptation. A multi-ton sauropod could essentially maintain a constant, warm internal temperature simply by existing, trapping the ambient heat alongside the massive thermal output generated by its immense digestive fermentation vats. This biological loophole allowed them to operate at the high metabolic speeds of a mammal while consuming significantly fewer calories per pound of body weight, making extreme gigantism thermodynamically viable. At a planetary scale, this metabolic revelation carries profound implications that extend far beyond paleontology. The transition from externally reliant temperature control to an internally generated metabolic furnace represents one of the most critical evolutionary thresholds in the history of any biosphere. In the context of astrobiology and the search for extraterrestrial intelligence, the development of endothermy is a strict prerequisite for planetary dominance. A cold-blooded biosphere is forever handcuffed to the diurnal cycles and latitudinal climate zones of its host star. Life shuts down in the dark and freezes at the poles, but the invention of the internal biological furnace severs that solar tether. It allows organisms to conquer the night, colonize the freezing extremes of high latitudes, and, most importantly, maintain the constant, uninterrupted high-energy supply required to power complex, sustained neural processing. If we apply this to the Fermi paradox, the capacity of a planetary biosphere to force its organisms across the thermodynamic gap from ectothermy to endothermy might be a critical great filter. A world that fails to develop internal metabolic regulation will never produce a species capable of advanced cognition or technological civilization. The histological data locked inside the fossilized bones of the Jurassic Period proves that dinosaurs were not evolutionary dead ends, lagging behind mammals. They were advanced, highly dynamic, high-revving biological engines that mastered planetary thermodynamics. This intense internal fire allowed them to grow from vulnerable hatchlings to massive, untouchable adults in a fraction of the time it would take a cold-blooded reptile, ensuring that by the time their environment stabilized, they had already grown entirely too fast and too large to be challenged by anything else on Earth. For over a century, the scientific establishment confined dinosaurs to a fundamentally flawed biological paradigm. Because they were taxonomically classified alongside modern reptiles, early paleontologists assumed they were strictly ectothermic, meaning they relied entirely on external solar radiation to regulate their core body temperature. Under this classical model, dinosaurs were envisioned as sluggish, slow-growing machines, their activity levels brutally dictated by the ambient temperature of their environment. However, this cold-blooded model completely collapsed when confronted with the biomechanical reality of the Jurassic Period. An ectothermic metabolism simply cannot generate the sustained, high-output kinetic energy required to support the massive anatomical frameworks of the apex predators. Nor could it mathematically explain the explosive growth rates necessary for the giant herbivores to survive their highly vulnerable juvenile stages. To resolve this profound thermodynamic paradox, modern science had to stop analyzing the macroscopic shape of fossilized skeletons and begin interrogating the microscopic architecture of the bone itself. This is the specialized field of paleohistology. Bone is not inert, dead scaffolding. It is a highly active biological hard drive that meticulously records the metabolic history of an organism throughout its entire life cycle. By extracting micro-thin cross-sections of fossilized femurs and analyzing them under polarized light, researchers can read the biological timeline of a dinosaur exactly like a climatologist reads the isotopic layers of an ancient ice core. What the microscopic data revealed shattered the reptilian model permanently. In modern cold-blooded reptiles, bone growth is slow, episodic, and heavily marked by dense, closely packed rings, known as lines of arrested growth. These lines indicate periods where the animal effectively shut down its metabolism to survive cold or dry seasons. But when scientists observed the cellular matrix of Jurassic dinosaurs, they discovered vast regions of fibrolamellar bone. This is a chaotic, rapidly deposited, highly vascularized type of tissue, woven with a dense, intersecting network of blood vessels. It is the unmistakable, irrefutable histological signature of aggressive, continuous biological construction. To lay down bone tissue at such an extreme velocity, the animal must possess a massive, relentless internal furnace. It requires an endothermic metabolism, warm-bloodedness. This discovery creates a direct conceptual bridge to the respiratory adaptations we examined earlier. The unidirectional breathing system, with its complex network of skeletal air sacs, was not merely a weight-saving measure. It was the absolute thermodynamic prerequisite required to supply the immense, continuous volumes of oxygen needed to fuel this raging internal fire. But biology rarely deals in binary absolutes, and the histological data introduced a complex new layer of scientific debate. While small, fast-moving predatory theropods showed clear signs of total endothermy, heavily resembling modern birds, some of the larger dinosaurs presented a physiological contradiction. Their bones displayed the rapid, highly vascularized growth of mammals during their juvenile stages, but as they reached adulthood, they retained distinct seasonal lines of arrested growth. This friction in the data birthed the hypothesis of mesothermy, an evolutionary middle ground. Under this model, dinosaurs generated vast amounts of internal metabolic heat to fuel rapid growth, but they did not strictly defend a single, unwavering core temperature. They allowed their internal thermostats to drift slightly with the seasons, saving massive amounts of caloric energy during ecological downturns, while still fundamentally outperforming any true cold-blooded competitor. For the colossal sauropods, the physics of thermodynamics shifted yet again, creating a phenomenon known as inertial homeothermy, or gigantothermy. When a biological machine reaches a certain extreme volume, the laws of physics dictate that its body simply cannot lose heat fast enough to cool down overnight. Their sheer physical mass became a primary evolutionary adaptation. A 30-ton sauropod could essentially maintain a constant, baking internal temperature simply by existing, trapping the ambient heat alongside the massive thermal output generated by its immense digestive fermentation vats. This biological loophole allowed them to operate at the high metabolic speeds of a mammal while consuming significantly fewer calories per pound of body weight, making their extreme gigantism thermodynamically viable. At a planetary scale, this metabolic revelation carries profound implications that extend far beyond paleontology into the realms of astrobiology and civilizational longevity. The transition from externally reliant temperature control to an internally generated metabolic furnace represents one of the most critical evolutionary thresholds in the history of any biosphere. A cold-blooded ecosystem is forever handcuffed to the diurnal cycles and latitudinal climate zones of its host star. Life shuts down in the dark and freezes at the poles. But the invention of the internal biological furnace completely severs that solar tether. It allows organisms to conquer the night, colonize the freezing extremes of high latitudes, and, most importantly, maintain the constant, uninterrupted, high-energy supply required to power complex, sustained neural processing. If we apply this to the Fermi paradox, the capacity of a planetary biosphere to force its organisms across the thermodynamic gap from ectothermy to endothermy might be a critical great filter. A world that fails to develop internal metabolic regulation will never produce a species capable of advanced cognition or technological civilization. The histological data locked inside the fossilized bones of the Jurassic Period proves that dinosaurs were not evolutionary dead ends lagging behind mammals. They were advanced, highly dynamic, high-revving biological engines that mastered planetary thermodynamics. This intense internal fire allowed them to grow from vulnerable hatchlings to massive, untouchable adults in a fraction of the time it would take a cold-blooded reptile, ensuring that by the time their environment stabilized, they had already grown entirely too fast and too large to be challenged by anything else on Earth. When we observe the fully articulated skeleton of a mature sauropod, we are looking at an organism that seemingly violates the fundamental laws of classical mechanics. The defining anatomical feature of these biological machines, a neck that could stretch over 30 feet from the shoulders, presents a profound physical paradox. In standard terrestrial biology, extending a lever arm of that immense length horizontally from a central fulcrum generates catastrophic rotational torque. Gravity dictates that such a structure should either instantly snap at the base or require a muscular suspension system so massive that the animal would be permanently paralyzed by the sheer weight of its own flesh. Yet sauropods not only carried these structures, they maneuvered them with calculated, fluid efficiency across the dense Jurassic landscape. The resolution to this paradox lies not in brute muscular strength, but in advanced biological architecture. If a sauropod neck were constructed using the dense, marrow-filled bone tissue characteristic of modern mammalian megafauna, it would be mathematically impossible to lift. Instead, the evolutionary pathway forged by the unidirectional respiratory system extended its influence directly into the skeletal framework. As the animal grew, the expansive network of respiratory air sacs aggressively invaded the cervical vertebrae. They excavated the solid bone from the inside out, carving complex networks of hollow chambers and microscopic, intersecting struts. The resulting spinal structure resembled a highly complex honeycomb, an intricate biological lattice that consisted of up to 60% empty airspace by volume. This extreme pneumatization drastically reduced the absolute mass of the neck while preserving its structure and integrity. When modern paleontologists subject digital models of these ancient vertebrae to finite element analysis, The exact same computational stress tests used by engineers to design modern skyscrapers and aerospace components. The results are staggering. The internal biological struts are aligned with such mathematical precision that they effortlessly distribute rotational and compressive forces away from the fragile neural canal. It is a perfect thermodynamic balance of maximizing compressive strength while ruthlessly eliminating every single ounce of redundant material. But reducing weight is only half the mechanical battle. The structure still must be actively supported against the constant, unrelenting downward pull of planetary gravity. To counter this, sauropods evolved a highly sophisticated biological tension system. A massive band of highly elastic connective tissue, known as the nuchal ligament, ran along the dorsal crest of the neck, permanently anchoring the back of the skull to the towering neural spines of the shoulders. This ligament functioned exactly like the main suspension cables of a modern bridge. It carried the massive tension load entirely passively. The dinosaur did not have to constantly fire muscle fibers and burn metabolic energy to hold its head up. The inherent elasticity of the ligament simply locked the neck in a resting, elevated position. Muscular energy was only expended when the animal needed to actively push its head down to drink water or reach lower foliage. This leads to a deeper consequence regarding the fundamental limits of biological design and genetic flexibility. Why have terrestrial mammals, in the 66 million years since the dinosaurs fell, never replicated this specific brand of extreme gigantism? The answer lies in rigid evolutionary constraints. The mammalian blueprint is genetically locked into possessing exactly 7 cervical vertebrae. To evolve a long neck, a modern giraffe cannot add more bones. It can only stretch the existing 7, resulting in a stiff, mechanically limited, and incredibly heavy structure. Sauropods were completely decoupled from this genetic restriction. They simply added more vertebrae, sometimes pushing the count up to 19, and elongated them simultaneously, achieving an unparalleled degree of mechanical reach and flexibility. At a planetary scale, the meaning of this anatomical divergence changes completely. The hyper-elongated neck was not merely a specialized feeding tool. It was the ultimate thermodynamic energy-saving mechanism. By parking its colossal, multi-ton body in one single location, a sauropod could sweep its head through a massive hemispherical volume of vegetation, stripping entire forest canopies bare without taking a single step. The caloric return on investment was astronomical. The chemical energy gained from the consumed flora vastly outpaced the minimal kinetic energy spent moving the lightweight pneumatic neck. This absolute mastery of energy extraction reveals a crucial threshold for any expanding species. A planetary biosphere is a closed thermodynamic system. If an organism expends more energy locating and harvesting food than the food itself provides, the lineage eventually collapses. The sauropod circumvented this limitation by turning itself into a stationary harvesting platform. In the context of the Fermi paradox, we often look for advanced alien civilizations that have maximized their planetary energy extraction, theorizing about megastructures capturing stellar radiation. The sauropod achieved a purely biological version of this maximization. They engineered a system that stripped maximum chemical energy from the environment while expending near-zero kinetic energy to acquire it. It was an ecological masterclass in resource management that allowed them to push the absolute physical limits of the biological carrying capacity of the Earth. And right here, this biomechanical hypothesis begins to connect with a much larger question about planetary biology across the universe. When astrobiologists model the potential for complex megafauna on exoplanets, especially those with high surface gravity, the sauropod blueprint becomes the absolute baseline requirement. Dense, solid skeletons scale terribly under strong gravitational pull, To achieve extreme terrestrial size on any rocky world, a biosphere must engineer around the limits of solid matter. It must evolve a highly advanced form of biological pneumatization. The honeycomb vertebrae of the Jurassic sauropods demonstrate that nature's ultimate solution to gravity is not to build heavier bones, but to build structurally perfect voids. They were the most efficient biological machines ever to navigate a gravitational field, turning empty space into their absolute greatest evolutionary advantage. The extreme hyper-elongated architecture of the sauropod neck engineered a strict biomechanical limit on the design of the skull. To support a biological lever arm that could stretch over 30 feet from the shoulders, the weight at the absolute tip of that structure had to be ruthlessly minimized. This physical reality forced a radical evolutionary trade-off in how these animals consumed and processed energy. Modern mammalian megaherbivores, such as elephants or rhinos, rely on massive, dense blocks of molars to physically crush and pulverize plant matter before swallowing. This mechanical breakdown is powered by heavily anchored jaw muscles and a thick, heavily reinforced skeletal cranium. If a sauropod possessed a mammalian chewing apparatus, the sheer gravitational weight of the skull would cause the delicate pneumatic suspension system of the neck to completely collapse under its own torque. Consequently, sauropods completely abandoned the act of mastication. Their skulls shrank to disproportionately tiny, lightweight dimensions relative to their colossal bodies. They were equipped only with simple, peg-like or spoon-shaped teeth located strictly at the front of the mouth. These teeth were designed exclusively to strip foliage from branches and swallow it entirely whole, functioning less like a complex mouth and much more like a biological harvesting rake. For decades, paleontology assumed that because they swallowed vegetation intact, sauropods must have utilized a brutal biological grinding mill inside their stomachs to break down the food. Scientists theorized they relied on intentionally swallowed stones, called gastroliths, to mechanically pulverize the plant matter inside a highly muscular gizzard, utilizing a mechanism identical to modern ostriches. But modern taphonomic data and high-resolution microscopic analysis have fundamentally disrupted this classical model. When researchers closely examine the surface textures of suspected gastroliths found alongside articulated sauropod skeletons, the stones almost universally lack the severe microscopic pitting, fracturing, and high-polish friction marks that would be inherently present if they were violently grinding against rough, silica-rich plant fiber in a muscular sac. This discrepancy triggers a significant scientific debate regarding chemical extraction. The current, more robust alternative hypothesis suggests these stones may have simply been ingested accidentally during aggressive, high-volume mass feeding. Alternatively, they were deliberately swallowed not for grinding, but to act as a slow-release source of vital dietary minerals, gradually dissolving in deep stomach acids to supplement a calcium-poor gymnosperm diet. If mechanical grinding was entirely abandoned, the extraction of caloric energy had to be an exclusively chemical process. The swallowed gymnosperm foliage, heavily armored with toxic secondary resins and rigid crystalline cellulose, was transported into the single largest biological processing facility terrestrial evolution has ever produced. Sauropods relied almost exclusively on hindgut fermentation. Their abdominal cavity housed intestinal tracts so incredibly voluminous that plant matter could be retained for weeks at a time without moving. Within these dark, low-oxygen vats, a microscopic alien ecosystem of trillions of symbiotic bacteria slowly dismantled the tough plant cell walls. Vertebrates fundamentally cannot produce the specific enzymes required to digest cellulose. The true biological supremacy of the dinosaur was its ability to house, manage, and fuel an internal microbial empire that executed the heavy chemical lifting for them. This specific digestive mechanism is strictly governed by the unyielding laws of thermodynamics. Bacterial fermentation of tough, woody fiber generates immense amounts of excess metabolic heat. In a smaller animal, this thermal byproduct would easily dissipate into the surrounding air, but within the colossal, perfectly insulated bulk of a 30-ton sauropod, the heat was permanently trapped deep inside the core. This internal furnace maintained the bacterial colonies at peak metabolic efficiency, regardless of dropping environmental temperatures outside. It represents a flawless biological feedback loop. The extreme gigantism of the animal provided the vast physical space required to house the massive fermentation gut, and the fermentation process itself generated the deep, stable internal heat that made that extreme gigantism thermodynamically viable. But engineering a multi-ton biological machine focused entirely on continuous chemical processing creates a severe ecological vulnerability. Maintaining this massive internal ecosystem requires a relentless, unbroken influx of external calories. This biological reality leaves almost zero margin in the energy budget with the immense metabolic cost of reproduction. If a mature sauropod attempted to reproduce using the standard mammalian strategy, the results would be anatomically and energetically impossible. Mammals generally employ a reproductive strategy known as K-selection. They invest an enormous amount of biological capital into a very small number of offspring, gestating them internally for extended periods and feeding them high-calorie milk long after birth. If a female sauropod were to carry a fetus proportional to her adult size, the gestation period would theoretically stretch for years. This prolonged pregnancy would permanently compromise the mother's mobility, and passing a massive infant would require a pelvic canal so wide it would physically shatter the biomechanical architecture of her hind legs, destroying her ability to support her own weight. Furthermore, the caloric drain of internally nursing a giant, fast-growing infant would easily outpace the maximum energy output her fermentation gut could physically process. The mammalian reproductive model simply breaks down at the scale of extreme megafauna. To bypass this absolute reproductive bottleneck, sauropods utilized a highly extreme version of an alternative evolutionary strategy known as R-selection. They completely detached adult energy expenditure from juvenile development. A single female sauropod would lay clutches containing dozens of relatively small, spherical eggs. Observational data from massive fossilized nesting grounds, such as the Alcamahuevo site in South America, reveals that these animals often returned to communal breeding areas year after year, depositing hundreds of offspring over a lifetime. But why were the eggs so small? The size of a biological egg is strictly governed by the physics of gas diffusion. The shell must be porous enough to allow oxygen to flow in and carbon dioxide to flow out. If an egg grows too large, its volume increases much faster than its surface area. The embryo would literally suffocate inside its own shell before it could hatch. Therefore, even a colossal sauropod was constrained by physics to lay an egg no larger than a modern soccer ball. This created an extreme biological scaling factor. A hatchling emerged at a fraction of a percent of its mother's size. Once the eggs were buried in the warm earth or decomposing vegetation, parental investment instantly dropped to zero. The adults simply turned around and walked away, leaving the embryonic development entirely to the ambient thermal energy of the environment. This mass production strategy created a brutally steep mortality curve. The vast majority of sauropod hatchlings emerged into a world heavily populated by hyper-efficient theropod predators and were consumed within their first few months of life. They functioned as the primary biological fuel that sustained the entire carnivorous ecosystem of the Jurassic. But from the perspective of population genetics, this strategy is incredibly robust. By producing overwhelming numbers of offspring, the species mathematically guaranteed that a tiny fraction would survive the gauntlet of predation long enough to reach an impregnable adult size. This leads to a much deeper consequence when viewed through the lens of deep time and planetary extinction cycles. A K-selected mammalian species requires decades to replace a lost generation. If a localized environmental disaster wipes out the adult breeding population, the entire species collapses because their slow reproductive rate cannot outpace the mortality rate. But a population of R-selected sauropods could endure staggering, catastrophic losses. As long as a tiny handful of adults survived an ecological crisis, they possessed the biological capacity to flood the recovering environment with thousands of new offspring in a single season, rebounding with terrifying demographic elasticity. And right here, this ancient biological reproductive model connects directly with the broader concepts of astrobiology and civilizational longevity. When modeling the survival probability of complex biospheres across millions of years, the method of genetic transmission is the ultimate determinant of resilience. A species that biologically hardwires itself to rapid, high-volume reproduction achieves an extreme degree of survivability. The sauropods ruled the planet not simply because they were too physically large to kill, but because their underlying genetic architecture was designed to absorb immense casualties and instantly repopulate, mastering both the extreme mechanical limits of individual gigantism and the ruthless efficiency of mass duplication. The geological record of Western North America contains a vast, continuous layer of sedimentary rock known as the Morrison Formation. In paleontology, the Morrison is not simply a rock sequence. It is a high-fidelity biological hard drive that recorded the absolute climax of the Jurassic Period. The fossil data extracted from these ancient floodplains and riverbeds presents an enormous ecological paradox. Within this single geological formation, scientists have uncovered the remains of an impossibly dense concentration of megafauna. Colossal herbivores like Brachiosaurus, Diplodocus, Apatosaurus, Stegosaurus, and Camarasaurus were all living simultaneously in the exact same geographical region. In any modern ecosystem, placing multiple species of multi-ton herbivores in the same environment results in rapid and catastrophic overgrazing. The carrying capacity of the land simply shatters under the immense thermodynamic demand. Yet, the Morrison data indicates this massive biological community remained highly stable for over 10 million years. This forces a fundamental re-evaluation of how energy moves through a biosphere. An ecosystem is ultimately a closed thermodynamic system. The primary producers, the gymnosperms and ferns, convert solar radiation into chemical energy. If the extraction rate by herbivores exceeds the biological replacement rate by plants, the system experiences a trophic collapse. The sustained survival of the Morrison megafauna proves that they were not directly competing for the exact same calories. Instead, they utilized a highly advanced ecological strategy known as niche partitioning. They divided the environment into distinct, non-overlapping zones of exploitation, transforming a two-dimensional landscape into a highly efficient, three-dimensional grid of energy extraction. The first layer of this division was strictly vertical. Brachiosaurus was biologically engineered for upward mobility. Its forelimbs were significantly longer than its hind limbs, permanently tilting its entire torso upward and positioning its massive neck to graze exclusively on the highest canopies of the conifer forests, reaching altitudes of over 40 feet. By feeding at this extreme elevation, it completely bypassed the vegetation below, isolating its calorie source from every other herbivore on the ground. This physical verticality artificially expanded the usable volume of the biosphere, allowing the environment to support a vastly greater amount of absolute biomass without increasing the physical footprint of the land. Beneath the canopy, The horizontal sweep of the understory belonged to the diplodocids. The skeletal architecture of Diplodocus was fundamentally different. Its neck was positioned to extend forward, parallel to the ground, counterbalanced by an incredibly long, whip-like tail. It functioned as a biological scythe, sweeping across massive arcs of low-lying ferns and horsetails. Even closer to the soil, Stegosaurus operated at the absolute ground floor, equipped with a low-slung head and a narrow beak, perfectly adapted for selectively cropping specific, low-energy cycads that the larger sauropods simply ignored. They all shared the exact same physical square footage, but structurally, they lived on entirely different floors of the same ecological building. But the division of resources went much deeper than physical height. It was also mechanical and chemical. When researchers perform microscopic analysis on the tooth wear patterns and measure the carbon and oxygen isotopes locked inside the fossilized enamel, they find that even dinosaurs feeding at similar heights were processing entirely different materials. Camarasaurus possessed thick, robust, spoon-shaped teeth set into a heavily built, powerful skull. This biomechanical hardware allowed it to forcefully snap off thick branches and consume incredibly tough, woody material. In stark contrast, Diplodocus possessed delicate, pencil-like teeth situated only at the very front of its mouth. It could not physically snap branches. Instead, it used its teeth like a biological comb, delicately stripping soft needles and young leaves from stems without damaging the underlying plant structure. This level of hyper-specialization, however, introduces a profound systemic vulnerability. A biosphere built on extreme niche partitioning is highly efficient, but utterly rigid. If a prolonged drought or a sudden climate shift destroyed the specific high canopy conifers that Brachiosaurus relied upon, the animal could not simply adapt to eating low-lying ferns. Its anatomical hardware made that physically impossible. To mitigate this catastrophic risk, the Morrison ecosystem utilized dynamic temporal partitioning. Isotopic strontium data extracted from fossilized sauropod teeth act as a geochemical tracking system, revealing that these multi-ton machines did not stay in one place. They undertook massive, seasonal migrations spanning hundreds of miles following the shifting monsoon rains across the continent. By constantly moving, they actively prevented the total depletion of any single localized feeding zone, granting the slow-growing gymnosperms the crucial time needed to regenerate their biomass. And right here, this ancient ecological model connects directly with the larger questions of astrobiology and the longevity of advanced civilizations. When we look at the universe and calculate the probability of long-lasting extraterrestrial biospheres, the carrying capacity of a planet is always the ultimate limiting factor. The Morrison Formation proves that a planet's biological limit is not dictated solely by the raw amount of solar energy it receives, but by the mathematical efficiency with which life divides and utilizes that energy. A successful, deep-time biosphere must eventually achieve perfect niche partitioning, eliminating zero-sum competition for identical resources. If we apply this to the concept of the Great Filter, perhaps the true test for any expanding technological civilization is whether it can transition from aggressive, overlapping resource competition to a perfectly partitioned, sustainable extraction model. The Jurassic megaherbivores managed their planetary resources with such mechanical precision that they sustained maximum biological capacity for millions of years, an ecological masterclass that modern human civilization is still attempting to understand. The sauropods achieved planetary dominance through the sheer physical volume of their biological infrastructure. But they were not the only herbivores adapting to the hyper-arid, high carbon dioxide environment of the deep Jurassic. The ornithischians, or bird-hipped dinosaurs, took a fundamentally different evolutionary pathway. Instead of stretching their biology to the absolute physical limits of gigantism, they invested their metabolic surplus into radical anatomical modifications, specifically dermal armor and highly specialized skeletal structures. The most iconic representation of this biological engineering strategy during the late Jurassic was Stegosaurus. However, the exact mechanical function of its most defining feature, the alternating double row of massive kite-shaped plates running down its spine, has triggered one of the most intense and enduring debates in modern paleontology. For decades, the default scientific assumption was that these plates served as heavy biological armor, a direct physical defense mechanism against the apex predators of the era. But when modern biomechanical engineers subjected fossilized plates to structural stress tests, the armor hypothesis completely collapsed. These plates were not directly fused to the skeletal spine. They were simply embedded deep within the skin, a type of structure technically known as an osteoderm. A lateral strike from a 2-ton theropod would easily snap them off at the base. Furthermore, microscopic analysis revealed that the internal structure of the plates was not dense, impact-resistant bone. Instead, it was highly porous, fragile, and constructed almost exactly like a rigid sponge. From a purely defensive standpoint, exposing the largest, most fragile biological surface area on the absolute highest point of the body is a fatal design flaw. To resolve this mechanical paradox, researchers turned to paleohistology and high-resolution scanning technologies. When they mapped the internal cavities of the plates, they discovered an incredibly vast, intricate, and highly organized network of tubular channels. These were not random voids created by bone degradation. They were the structural housing for a massive, active vascular system. During the animal's life, a tremendous volume of blood was continuously pumped directly from the core of the body up into these external plates. This biological reality fundamentally changes the function of the structure. A living organism does not pump immense volumes of vital blood into an exposed, easily damaged outer shield, unless the physiological payoff is absolutely critical to its survival. This discovery led to the development of the biological radiator hypothesis. As established earlier, generating internal heat through rapid metabolism or massive digestive fermentation creates a critical thermal challenge, the severe risk of overheating. The plates of Stegosaurus offered a highly sophisticated thermodynamic solution. By actively controlling the dilation and constriction of the blood vessels within the plates, the animal could regulate its internal core temperature with astonishing precision. If the dinosaur was overheating, it could flood the large, flat surface area of the plates with hot blood, rapidly radiating excess thermal energy away into the cooler ambient air. The thermodynamics of this process are highly efficient, but they require an incredibly powerful, bird-like, four-chambered heart to maintain the immense blood pressure required to push fluid against gravity into the dorsal plates without compromising blood flow to the brain. Conversely, during the cooler mornings, the animal could orient its body perpendicular to the sun, using the plates as massive biological solar panels to absorb thermal radiation and kickstart its resting metabolism. But the scientific debate does not stop at simple fluid dynamics and heat exchange. A competing and increasingly supported model suggests that this extreme vascularity was utilized for active visual display. If Stegosaurus could rapidly pump high volumes of blood into the vessels just beneath the thin, translucent keratin sheath that likely covered the bone, it could cause the plates to suddenly flush with intense, brilliant color. This biological mechanism, known as vasodilation flushing, is used by many modern species for threat displays, allowing them to intimidate territorial rivals or deter predators without ever resorting to the extreme energy expenditure and physical risk of actual combat. This mechanism of active flushing extends far beyond Stegosaurus. As the Jurassic gave way to the Cretaceous, this exact biological hardware was adopted and scaled up by the ceratopsians, the horned dinosaurs like Triceratops. Their massive cranial frills, often assumed to be solid bone shields protecting the neck, were similarly heavily vascularized and covered in keratin. They were not just physical barricades, they were massive, highly active biological billboards. Even more critically, this mechanism serves as a powerful engine for sexual selection. In the high-stakes biological economy of these ancient ecosystems, demonstrating the capacity to grow and maintain such a massive, metabolically expensive, and highly visible structure signaled superior genetic fitness to potential mates. Sexual selection is recognized as one of the most powerful and reckless evolutionary drivers in nature, frequently pushing anatomical features to extreme, borderline maladaptive limits, simply to secure reproductive success. At a planetary scale, the meaning of these extreme anatomical structures changes completely. When astrobiologists model the evolutionary pathways of complex life on other worlds, they must account for how a species allocates its finite biological energy budget. Evolution is a ruthless accountant. Every calorie spent growing a massive thermal radiator, an elaborate biological billboard, or a heavily vascularized cranial frill is a calorie that cannot be invested in expanding the neural cortex. This creates a fascinating conceptual bridge to the Great Filter and the apparent rarity of technological civilizations in the universe. A planetary biosphere might easily generate incredibly complex, highly active megafauna, but if the evolutionary pressure consistently rewards extreme physical armaments and sexual displays over cognitive processing, the biosphere becomes trapped in a perpetual loop of physical optimization. Perhaps the true barrier to the emergence of intelligence is not surviving sudden planetary disasters, but escaping the relentless, internal biological arms race of physical display. The Ornithischians achieved incredible evolutionary success, not by growing the largest brains, but by turning their own bodies into the most sophisticated thermodynamic and visual machines on the planet. Their plates and horns were not primitive, clumsy armor. They were highly active, multifunctional biological instruments that perfectly balanced the brutal demands of internal temperature regulation, species recognition, and mate selection, ensuring their lineage would thrive and rapidly diversify across the fracturing continents. The vast, walking mountains of biological energy represented by the sauropods did not exist in an ecological vacuum. Where immense calories accumulate within a biosphere, the laws of thermodynamics dictate the inevitable emergence of biological mechanisms designed to forcefully extract them. The late Jurassic period engineered an entirely new class of apex predators to fulfill this role: the giant theropods. Within the Morrison ecosystem, the fossil record reveals a terrifyingly crowded landscape of terrestrial carnivores. Massive killers like Ceratosaurus, Torvosaurus, and the undisputed apex of the era, Allosaurus, all patrolled the exact same geographic territory. In modern mammalian ecosystems, placing multiple hypercarnivores in the same environment inevitably leads to aggressive competitive exclusion, a scenario where one species eradicates or completely outstarves the others. The fact that these massive theropods coexisted in a highly stable ecosystem for millions of years indicates a strict biomechanical division of labor. They were not fighting over the exact same prey, using the exact same anatomical weapons. To understand how they carved up the ecosystem without destroying it, Science had to look beyond the macroscopic shape of their teeth and peer directly into the physics of their skeletal architecture. For decades, the predatory mechanics of giant theropods were deeply misunderstood. Scientists assumed they operated exactly like modern mammalian apex predators, relying on overwhelming jaw strength to clamp down, crush thick bone, and physically drag struggling prey to the dirt. But when modern biomechanical engineers placed the fossilized skull of an Allosaurus into a supercomputer and subjected it to finite element analysis, the exact mathematical and computational tool used to test the stress tolerance of modern jet engine turbine blades, the results completely shattered the classical predatory model. The computational simulations generated a profound biomechanical paradox. Based on the physical volume of the jaw muscles and the angle of biological leverage, the sustained bite force of a fully grown 2-ton Allosaurus was mathematically proven to be astonishingly weak. It exerted significantly less bite pressure than a modern American alligator, an animal a mere fraction of its size. If a predator relies on its mouth as its primary tool of execution, but cannot generate the sheer mechanical force to crush bone or physically anchor itself to a struggling 30-ton sauropod, the evolutionary design appears to be a fatal biological failure. However, the computer models revealed a secondary, hidden layer of biological engineering. While the bite force was remarkably weak, the structural architecture of the skull itself was wildly over-engineered to resist a completely different type of mechanical stress. The cranium of Allosaurus was built to absorb immense, catastrophic vertical shock without fracturing or transferring lethal concussive force into the brain cavity. Furthermore, its jaw joints possessed an extreme range of motion, allowing the animal to open its mouth to an impossibly wide angle, completely clearing its lower jaw out of the way of its upper teeth. This precise combination of weak bite force, extreme vertical shock absorption, and massive gape birthed the hatchet attack hypothesis. Under this model, Allosaurus did not bite and hold its prey. It weaponized its entire skull as a massive kinetic instrument. The animal would accelerate towards its target, open its jaws to maximum extension, utilize its heavily muscled, highly robust neck, and slam its upper jaw forcefully downward into the flesh of its victim. The serrated, blade-like teeth acted exactly like the cutting edge of a biological hatchet. Instead of crushing, it slashed deeply through thick muscle and major arteries, instantly retreating to let catastrophic blood loss and hydrostatic shock do the actual killing. This leads to a much deeper consequence regarding the physics of biological combat and material science. The hatchet attack method is a masterpiece of kinetic energy transfer, but it carries an extreme inherent risk. Slamming a high-velocity skull into a moving, heavily armored target means that if the predator misses the soft tissue and strikes solid bone, the resulting mechanical rebound could instantly snap its own neck or shatter its teeth. This reveals a strict limitation in biological weapon design. Evolution can optimize an organism for lightning-fast, slashing speed, or for slow, bone-crushing power. But the unyielding laws of physics heavily penalize attempting to do both simultaneously without completely compromising the structural integrity of the skull. But the problem does not stop at the mechanics of a single species. By utilizing this hit-and-run slashing tactic, Allosaurus completely avoided the need to physically grapple with animals 10 times its mass, a strategy that would mean certain death. It specialized in bleeding out massive prey. Meanwhile, its contemporary, Ceratosaurus, possessed vastly longer teeth and a different skull stress profile, suggesting it targeted smaller, softer prey, or focused on deep puncture ambush tactics. Torvosaurus, built with a heavier, more robust frame, likely occupied the brute force niche, scavenging or taking down heavily armored targets that the lighter Allosaurus actively avoided. They successfully divided the carnivorous ecosystem through extreme biomechanical specialization. At a planetary scale, the meaning of this predatory engineering alters our understanding of evolutionary time. In the modern fields of astrobiology and the modeling of hypothetical alien biospheres, the existence of a highly efficient, mechanically diverse predator class is considered absolutely essential for long-term planetary development. Predators are the ultimate biological catalysts. They introduce the constant threat of sudden, violent energy extraction, which forces prey species to innovate aggressively. Without the ruthless pressure applied by biological machines like Allosaurus, the massive herbivores would stagnate, halting the development of thicker armor, faster reflexes, and eventually more complex neurological processing. And right here, this hypothesis begins to connect with the larger questions of the Great Filter and the emergence of advanced intelligence in the universe. A biosphere trapped in a peaceful equilibrium, completely devoid of top-tier biological threats, never experiences the brutal evolutionary arms race necessary to push the boundaries of neural capacity. The terrifying, mechanized precision of the Jurassic theropods was not simply an era of extreme violence. It was the essential thermodynamic engine of biological progress. By constantly testing the structural and chemical limits of the herbivores, these apex predators guaranteed that the global biosphere remained in a perpetual state of hyper-adaptation, laying the critical evolutionary groundwork required for the even more extreme biological architectures that would eventually rise to dominate the Earth. For decades, popular culture has aggressively promoted a very specific, terrifying image of theropod dinosaurs, the highly coordinated, wolf-like pack. It is a compelling cinematic narrative to imagine a squad of apex predators communicating, flanking, and executing complex tactical maneuvers to take down massive sauropods. But when this assumption is subjected to the rigorous, unforgiving scrutiny of modern paleoneurology, the entire behavioral model completely breaks down. To truly understand how the carnivores of the Jurassic ecosystem interacted with each other and their prey, science had to look past the lethal architecture of their jaws and peer directly into the empty spaces of their fossilized skulls. Brain tissue decays within days of an animal's death, but the rigid bone of the brain case remains, acting as a perfect three-dimensional mold. By utilizing high-energy, X-ray microcomputed tomography, or CT scanning, paleontologists can digitally reconstruct the exact size, shape, and volumetric distribution of a dinosaur's brain. The resulting digital model, known as an endocast, provides a direct map of the animal's biological hardware. When researchers analyze the endocasts of late Jurassic theropods, like Allosaurus or Ceratosaurus, the data reveals an organism hyper-optimized for individual sensory input. The olfactory bulbs, the neurological centers dedicated strictly to processing smell, are absolutely immense, occupying a massive percentage of the overall brain volume. These animals were essentially biological guided missiles, equipped with state-of-the-art chemical tracking systems capable of detecting the volatile organic compounds of decaying flesh or fresh blood from miles away across the dense conifer forests. However, the CT scans also expose a strict, insurmountable biological limitation. While their sensory processing was exceptional, the cerebrum, the region of the brain responsible for higher-order cognitive functions, social processing, and strategic anticipation, was relatively small and structurally simplistic. This neurological reality creates a hard barrier against the pack hunting hypothesis. True coordinated hunting, as observed in modern mammalian apex predators like African wild dogs or orcas, requires an incredibly demanding set of cognitive algorithms. An animal must be capable of holding a mental model of its pag meat, predicting their movements, communicating tactical shifts in real time, and, most importantly, suppressing its own immediate biological drive to feed in order to execute a trap. The Endocast data mathematically dictates that the theropod neural hardware simply lacked the raw processing capacity to run this kind of complex, cooperative, social software. But this raises a massive observational paradox in the geological record. If they did not form coordinated packs, how does science explain the existence of massive fossil graveyards, like the famous Cleveland Lloyd dinosaur quarry in Utah? At this single geographical site, paleontologists have uncovered the remains of over 40 individual Allosaurus, tangled together in a dense, chaotic geological deposit. If they were solitary killers, what biological mechanism forced them into such extreme proximity? The resolution to this paradox lies in an alternative behavioral model known as mobbing, or uncoordinated aggregation. Instead of acting like a wolf pack, Jurassic theropods operated much more like modern Komodo dragons or crocodilians. The Cleveland Lloyd site was not a communal den. It was a lethal predator trap. When a massive herbivore became fatally mired in the deep, sticky mud of a drying floodplain, its struggles and subsequent death transformed it into a massive biological beacon. The intense chemical signature of the rotting carcass drifted downwind, triggering the hypersensitive olfactory bulbs of dozens of solitary predators across the landscape. They were all drawn to the exact same location, not out of social cohesion, but out of pure, overlapping, selfish interest. Once they arrived at the carcass, the resulting interaction was not a coordinated communal feast, but a violent, chaotic feeding frenzy. The predator trap claimed the herbivores, and then it systematically claimed the carnivores that came to feed on them, slowly stacking bodies over decades. The fossilized bones of Allosaurus found in these deposits frequently show deep gouges, healed puncture wounds, and severe traumatic injuries inflicted by the teeth of their own species. This undeniable evidence of intense intraspecies aggression confirms that the kill site was a biological free-for-all. The largest, most physically powerful individuals dominated the center of the carcass through sheer physical intimidation, while smaller juveniles and subadults frantically darted around the margins, attempting to tear off flesh without being killed and cannibalized by the adults. It was a proximity-based exploitation system that might look like a pack from a distance, but was actually a highly dangerous, fundamentally solitary competition for extreme caloric reward. At a planetary scale, the meaning of this neurological limitation completely alters our perspective on the evolution of complex life in the universe. When astrobiologists and scientists engaged in the search for extraterrestrial intelligence attempt to identify the Great Filter, the theoretical evolutionary barrier that prevents life from developing advanced technology, the transition from solitary computation to social intelligence is considered one of the most critical thresholds in existence. The Jurassic ecosystem proves a profound astrobiological point. A planet can spend millions of years engineering the most biomechanically perfect, physically dominant predators the universe has ever seen, yet remain completely stagnant in terms of civilizational progress. Biological hardware optimized purely for solitary energy extraction and immediate sensory reaction is an evolutionary dead end for higher consciousness. Empathy, social coordination, and cooperative problem-solving are incredibly expensive metabolic investments. Unless a planetary environment applies a specific, unrelenting pressure that forces a species to abandon the selfish feeding frenzy and invest its caloric surplus into social neural architecture, a technological civilization will never emerge. The apex predators of the Jurassic mastered the physical mechanics of their world with terrifying efficiency. but they were permanently locked out of the cognitive universe by the strict, unyielding limitations of their own fossilized brains. While the massive sauropods and heavily armed theropods fought a brutal, endless war for control of the two-dimensional terrestrial landscape, an entirely separate lineage of archosaurs initiated the conquest of a completely different physical realm: the third dimension. It is a critical scientific distinction that must be established immediately to understand the evolutionary history of the planet. The creatures that ruled the Jurassic skies were not dinosaurs. They were Pterosaurs, a distinct but closely related sister clade that diverged millions of years earlier. The biological challenge they faced was fundamentally different from their ground-dwelling cousins. To conquer the air, an organism cannot simply grow larger, develop thicker armor, or run faster. It must actively and continuously defeat the unrelenting downward pull of planetary gravity. This requires a radical, uncompromising redesign of terrestrial anatomy. When we examine the fossilized skeletal architecture of a pterosaur, we bear witness to one of the most extreme structural modifications in vertebrate history. Modern flying vertebrates have adopted different biomechanical solutions for achieving flight. Birds fuse their arm bones and use rigid interlocking feathers to generate an aerodynamic surface. Bats extend all of their fingers to stretch a thin, highly flexible web of skin. But pterosaurs engineered a completely unique biomechanical apparatus. They ruthlessly minimized their forelimbs and isolated a single digit. The fourth finger, the anatomical equivalent of the human ring finger, was elongated to absurd, disproportionate lengths. In some advanced Jurassic species, this single finger grew longer than the entire combined length of the animal's torso and hind legs. This hyperextended digit served as the primary biological spar, supporting a massive aerodynamic sail known as the patagium. But for decades, scientists incorrectly visualized this membrane as a simple, dead flap of leathery skin, much like a passive kite. Modern microscopic analysis of exceptionally preserved fossils from fine-grained limestone deposits has completely overthrown this assumption. The wing membrane was packed with a dense, intersecting network of stiff, microscopic structural cables called actinofibrils. These internal fibers, embedded directly within the skin, allowed the pterosaur to actively control the tension, camber, and aerodynamic profile of its wing in real time. By subtly flexing microscopic muscles within the membrane, the animal could instantly shift from a high-lift, highly curved configuration to catch slow thermal updrafts to a flat, low-drag profile for high-speed directional pursuit. It was not a passive sail. It was a living, breathing aerodynamic surface that functioned with the dynamic precision of a modern aircraft wing. But the mechanical structure of the wing is only half the equation of powered flight. The other half is strictly governed by the brutal, unforgiving laws of thermodynamics. Powered flight is the single most metabolically expensive form of sustained locomotion in the biological universe. Flapping massive wings against the resistance of the atmosphere requires an unimaginable burn of caloric energy and a continuous, uninterrupted supply of pure oxygen. Furthermore, the atmosphere is a hostile thermal environment. As altitude increases, ambient temperature drops precipitously. It is physiologically impossible to power a flying machine of this scale using the slow, environmentally dependent metabolism of a cold-blooded reptile. If a pterosaur relied on the ambient heat of the sun to warm its muscles, it would rapidly freeze and plummet from the sky the moment it entered the frigid air of high altitudes or flew into the freezing shadow of a massive storm cloud. To resolve this metabolic paradox, paleontologists searched for the biological signature of an internal furnace. They found it perfectly preserved in the deep fossil record. Under ultraviolet light and high-powered electron microscopes, researchers discovered that the bodies of pterosaurs were not covered in reptilian scales. They were densely wrapped in a thick coat of hair-like filaments known as pycnofibers. This structure is completely distinct from mammalian hair or avian feathers, representing an incredible instance of convergent evolution, where nature engineers a highly specific, identical solution to a universal physical problem across entirely unrelated genetic lineages. The presence of pycnofibers is the absolute, irrefutable smoking gun for endothermy, warm-bloodedness. In the strict, unforgiving economy of biological engineering, an organism does not invest the massive metabolic resources required to grow and maintain a dense insulating coat unless it possesses a powerful internal heat source that absolutely must be protected from the external environment. The pycnofibers trapped a microscopic layer of dead air against the skin, completely insulating the pterosaur's extreme metabolic core from the freezing temperatures of the upper atmosphere. This allowed them to operate their biological flight engines at maximum capacity, entirely independent of the ambient planetary temperature. At a planetary scale, the meaning of this fibrous covering completely alters our understanding of evolutionary potential and civilizational expansion. In the fields of astrobiology and the theoretical modeling of extraterrestrial biospheres, the transition from terrestrial crawling to powered flight is considered a massive evolutionary filter. A planet's atmosphere offers a vast, frictionless medium for travel, rapid colonization, and predator evasion. But accessing it requires a species to cross a terrifying thermodynamic threshold. If a planetary environment cannot supply the extreme caloric density and oxygen concentration required to fuel an internal biological furnace, its animal life will remain permanently locked to the dirt, unable to fully exploit the physical volume of their world. The pycnofibers of the pterosaurs prove that flight is not merely a mechanical trick of elongated bones and stretched skin. It is the ultimate triumph of internal metabolic engineering over physical environment. By generating their own immense heat and weaving their own atmospheric insulation, these flying reptiles permanently severed their biological dependence on the physical surface of the Earth. They unlocked a boundless three-dimensional empire, turning the hostile, freezing skies of the Mesozoic into a permanent biological domain, millions of years before the first bird ever took to the air. While the skies above the fracturing supercontinent offered a seemingly boundless, frictionless empire for the pterosaurs, the global oceans of the deep Jurassic presented a fundamentally different physical barrier. Liquid water is approximately 800 times denser than the atmosphere. Any organism attempting to achieve high-speed pursuit in this environment is immediately confronted by the brutal, mathematically unforgiving laws of fluid dynamics. Drag increases exponentially with speed, meaning that any physical inefficiency, any protruding bone or blunt anatomical surface, instantly drains massive amounts of metabolic energy. A lineage of strictly terrestrial reptiles returned to the sea to exploit the rebounding marine food webs following the Triassic extinction. Over millions of years, they were subjected to the relentless sculpting force of hydrodynamic resistance. The resulting biological machines, the ichthyosaurs, represent one of the most profound examples of convergent evolution in the history of the planet. They abandoned their reptilian, lizard-like appearance entirely and developed a perfectly streamlined, fusiform torso, a dorsal fin constructed of dense connective tissue for stabilizing high-speed rolls, and a massive, crescent-shaped tail strictly powered by rapid lateral spinal flexion. If you examine the skeletal outline of a late Jurassic ichthyosaur and superimpose it over the skeleton of a modern great white shark or a mammalian dolphin, the biomechanical profiles are nearly identical. These animals share no recent common ancestor. They are separated by hundreds of millions of years, of distinct evolutionary history, operating on entirely different metabolic systems. Yet they arrived at the exact same anatomical design. This is because the design was not chosen by the animal's genetics. It was dictated by the medium. This leads to a profound consequence in the field of astrobiology and planetary modeling. Convergent evolution proves that biology is not endlessly random. It is strictly channeled by the unyielding laws of physics. If a robotic probe eventually penetrates the thick ice crusts of the moon's Europa or Enceladus and discovers a dark subsurface ocean supporting complex multicellular macropredators, the laws of fluid dynamics demand that those alien organisms will likely share the exact same hydrodynamic profile of an ichthyosaur. The teardrop shape is not a terrestrial accident. It is the universal mathematical solution to moving biological mass efficiently through a dense liquid medium anywhere in the cosmos. But the complete anatomical transition to a pelagic open ocean existence triggered a catastrophic biological paradox for these ancient reptiles. The defining characteristic of the entire reptilian lineage is the amniotic egg. The shell of a reptilian egg is highly porous, biologically engineered to allow oxygen to flow in and carbon dioxide to flow out in a dry atmospheric environment. If an amniotic egg is submerged in water, the microscopic pores flood, gas exchange halts immediately, and the embryo drowns within minutes. Modern sea turtles solve this reproductive bottleneck through a geographical compromise. They retain their terrestrial limbs, dragging their heavy, armored bodies onto sandy beaches to bury their clutches above the high tide line. But the ichthyosaur's absolute evolutionary commitment to hydrodynamic perfection made this compromise mathematically impossible. By transforming their limbs into rigid, highly specialized hydrofoils designed strictly for steering, they lost all muscular and skeletal capacity to support their own weight against gravity. If a fully grown ichthyosaur washed ashore, the immense, unsupported mass of its own body would instantly crush its internal organs. They were permanently exiled from the land, trapped in the water. To survive this paradox, they had to engineer a radical internal redesign. They bypassed the external egg entirely through the evolution of viviparity, or live birth. The females retained the embryos deep within their reproductive tracts, providing oxygen and vital nutrients directly through a highly specialized placental structure until the infants were fully developed and capable of independent survival in the open ocean. We know this not through theoretical modeling, but through some of the most dramatic and mathematically improbable observational data in the entire fossil record. In the dark, oxygen-deprived shale deposits of Holzmaden in Germany, paleontologists have uncovered the perfectly preserved remains of female ichthyosaurs that died in the exact moment of giving birth. These extraordinary fossils act as a frozen frame of biological mechanics, revealing a highly specific, life-saving adaptation. The infant ichthyosaurs are preserved emerging from the birth canal, tail first. This is not an anatomical accident. In mammalian terrestrial births, emerging head first is the standard biological protocol. But underwater, a head-first delivery would expose the infant's blowhole to the ocean before its body was fully free from the mother's musculature. The sudden shock of cold water would trigger an involuntary inhalation reflex, causing the newborn to suck in water and drown while still physically trapped in the birth canal. By reversing the delivery sequence to a breech position, the mother ensured that the infant's head was the absolute last part to enter the water. This precise timing allowed the newborn to immediately kick its tail, fire its muscles, and shoot directly to the surface for its first critical breath of atmospheric air. At a planetary scale, the meaning of this reproductive internalization completely alters how we view the expansion of life. The evolution of viviparity was the final mechanism that completely severed the biological tether to the continent. It allowed marine reptiles to abandon the shallow, dangerous coastal shelves and permanently colonize the vast, three-dimensional abyss of the global ocean. By carrying their highly controlled, internal reproductive environments with them, they transformed from localized coastal scavengers into the undisputed apex predators of the marine world. And precisely here, this biological mechanism connects with the great filter and the long-term survival of any technological civilization. The true barrier to conquering a new physical domain, whether it is the depths of a global ocean or the vacuum of deep space, is often not surviving its extreme external pressures. The ultimate test is possessing the biological or technological plasticity to completely internalize your life support and reproductive systems. A species cannot truly conquer the stars if it is permanently tethered to the surface of its homeworld to generate the next generation. The ichthyosaurs mastered their alien environment by becoming entirely self-contained, mobile biospheres, proving that absolute liberation from your origin point requires carrying your genesis with you. The geological record is notoriously hostile to the preservation of fragile biological structures. The overwhelming majority of paleontology is built upon the study of hard tissues, dense teeth, massive femurs, and thick armor plates, because the chaotic, high-energy environments of terrestrial death rapidly obliterate anything soft. But in the late Jurassic archipelago of what is now Bavaria, Germany, a highly specific geological anomaly created a perfect biological archiving system. The Solnhofen limestone deposits were formed in stagnant, hypersaline lagoons. The water at the bottom of these lagoons was completely anoxic, entirely devoid of the oxygen required to support the microscopic bacteria responsible for decomposition. When an organism fell into this chemical dead zone, it did not rot. It was entombed in microscopic, ultra-fine-grained sediment, preserving not just its skeleton, but the exact, high-fidelity impression of its most delicate exterior anatomy. It was within these limestone vaults that paleontology discovered what is arguably the single most important fossil in the history of evolutionary biology: Archaeopteryx. This creature represented a profound anatomical paradox. A structural analysis of its skeleton revealed the unambiguous architecture of a small, predatory theropod dinosaur. It possessed a long, rigid, bony tail, 3 clawed fingers on each hand, and a jaw lined with sharp, serrated teeth. Yet, perfectly preserved in the limestone surrounding its arms and tail, was the unmistakable imprint of fully developed, asymmetrical flight feathers. It was the ultimate biological bridge, the frozen, transitional moment where the lineage of terrestrial apex predators began its transformation into modern birds. But the existence of Archaeopteryx triggered a massive mechanical and theoretical debate regarding the precise mechanisms of evolution. The aerodynamic feather is arguably the most complex integumentary structure ever produced by vertebrate biology. It is a masterpiece of lightweight engineering, consisting of a central hollow shaft from which branch hundreds of interlocking barbs secured by microscopic hooklets. The evolutionary paradox, frequently weaponized by early critics of Darwinian theory, is the problem of the half-wing. If the sole evolutionary purpose of a feather is to generate aerodynamic lift, a primitive, partially evolved feather is completely useless for flight. It provides no biological advantage. Natural selection cannot plan millions of years into the future, slowly building a wing for an animal that currently lives exclusively on the ground. To resolve this paradox, science had to abandon the assumption that feathers evolved for flight. They had to look at the structure through the lens of thermodynamics. This introduces a critical evolutionary mechanism known as exaptation or pre-adaptation. This unyielding principle dictates that a biological trait, originally engineered by environmental pressure to solve one specific problem, can later be co-opted and radically repurposed to solve an entirely different physical challenge. As we established with the microscopic bone data of the larger dinosaurs, the theropod lineage was fueled by a high-revving, warm-blooded metabolism. But while multi-ton predators like Allosaurus could rely on their massive physical bulk to retain internal heat through inertial homeothermy, the smaller, highly agile theropods faced a lethal thermodynamic crisis. Small animals possess a very high surface area to volume ratio. They bleed their internal metabolic heat into the environment at a catastrophic rate. To survive the dropping nighttime temperatures of the Jurassic without freezing to death, they required a highly efficient, lightweight biological insulator. The primitive ancestors of feathers did not look like the flight feathers of a modern eagle. They evolved as simple, hollow, hair-like filaments of keratin, almost identical in structural function to the pycnofibers developed independently by the pterosaurs. These proto-feathers densely covered the bodies of small, running dinosaurs, engineered strictly to trap a microscopic boundary layer of stagnant air against the skin. This dead airspace effectively locked in the immense heat generated by their internal metabolic furnaces, preventing it from radiating away. Feathers did not evolve to conquer the sky. They evolved to survive the harsh thermal realities of the dirt. Once the genetic machinery to produce these keratinous filaments was successfully established, a secondary evolutionary driver took control of their design: sexual selection. The physical structure of the filaments began to broaden and branch, not for aerodynamics, but to act as a canvas for visual display. When modern scanning electron microscopes are aimed at exceptionally preserved fossilized feathers, they can actually detect the microscopic, fossilized remains of melanosomes, the biological organelles responsible for synthesizing pigment. By measuring the geometric shape and density of these melanosomes, physicists can map the exact colors these ancient dinosaurs displayed. The data reveals that many feathered theropods were covered in striking iridescent blacks, vibrant reds, and complex banded patterns. They were highly visual, deeply social animals, using advanced plumage to signal territorial dominance and secure reproductive mates. Only after millions of years of optimizing these structures for heat retention and visual display did evolution accidentally stumble upon their aerodynamic potential. A small, feathered theropod, leaping to catch an insect or scrambling up a steep incline to escape a larger predator, would inadvertently gain a fractional aerodynamic advantage from the extended surface area of its display feathers on its forelimbs. Over countless generations, the relentless pressure of survival slowly refined these structures, stiffening the central shafts and making them asymmetrical to generate true aerodynamic lift. At a planetary scale, the mechanism of exaptation completely alters our understanding of how complex life, and ultimately advanced civilization, navigates the universe. When astrobiologists consider the Great Filter and the probability of alien intelligence, the concept of linear, planned evolution is entirely discarded. A biosphere does not invent solutions from scratch. It ruthlessly scavenges its own biological history. The hardware designed strictly to trap body heat on a small Jurassic predator eventually became the exact biological technology required to master the atmosphere. If we apply this to the trajectory of a technological species, the implications are profound. The tools initially designed for basic planetary survival or terrestrial warfare must be incredibly plastic, capable of being radically repurposed for deep space exploration. The rocket engines designed to deliver ballistic payloads across a continent become the exact same engines that push a species out of its gravity well. The feathered theropods prove that the ultimate evolutionary advantage is not perfect, forward-looking design, but absolute adaptability. They demonstrate how a localized thermodynamic solution can unexpectedly unlock an entirely new dimension of physical existence, allowing a lineage of earth-bound killers to eventually inherit the skies. To possess the biological hardware of a wing is not the same as possessing the capacity for flight. The presence of aerodynamic feathers in the fossil record triggered one of the most polarizing and mathematically intense debates in modern evolutionary biology. Paleontologists, biomechanical engineers, and aerodynamicists found themselves deadlocked over a profound physical paradox. How exactly does a terrestrial biological machine generate the initial kinetic thrust required to shatter its gravitational tether to the Earth? This scientific friction fractured the community into two fiercely competing paradigms: the arboreal model and the cursorial model. The arboreal, or trees down, hypothesis is built upon a foundation of strict thermodynamic efficiency. In the unforgiving economy of biological energy, fighting gravity from a dead standstill is the most metabolically expensive action an organism can undertake. The arboreal model argues that early Paravians bypassed this massive energetic cost by utilizing the verticality of the dense Jurassic and early Cretaceous gymnosperm forests. By climbing into the high canopy, these animals converted their caloric energy into gravitational potential energy. When they leaped to chase prey or evade a larger predator, they simply allowed planetary mass to pull them downward, using their feathered forelimbs to increase drag and execute a controlled fall. This model received what appeared to be definitive, irrefutable proof with the discovery of Microraptor, a spectacularly preserved fossil from the deep strata of China. Microraptor possessed fully developed asymmetrical flight feathers, not just on its arms, but also on its hind legs, effectively operating as a biological biplane. Aerospace modeling of this four-winged architecture demonstrated that it was mathematically impossible for this animal to run on the ground without fatally tripping over its own rear feathers. It was an organism exclusively engineered for the canopy, built to launch from a high branch and glide silently across the forest gaps. For years, this discovery positioned the arboreal model as the undisputed mechanism for the origin of flight. But as the fossil dataset expanded, a catastrophic mechanical contradiction began to systematically dismantle the trees-down consensus. While highly specialized side branches like Microraptor were adapted for the trees, the absolute basal ancestors of modern birds were not. When engineers ran structural stress tests on the skeletons of the earliest known feathered theropods, the anatomy violently rejected an arboreal lifestyle. Their hind limbs were constructed with hyper-elongated metatarsals, fused ankles, and restricted hip joints. This is the unmistakable, highly specialized architecture of an obligate terrestrial sprinter. They completely lacked the rotational flexibility and opposable digits required to grip bark and scale vertical tree trunks. Their long, rigid, bony tails functioned exactly like the dynamic counterweights used by modern cheetahs during high-speed ground maneuvers. The vast majority of early avian ancestors were biomechanically locked to the dirt. This structural reality forced the revival of the cursorial, or ground-up, hypothesis. This model suggests that flight was engineered in the flat, open floodplains. As these small theropods accelerated to maximum bipedal velocity to hunt insects or flee larger predators, they began to outstretch their feathered arms to maintain lateral stability. According to this theory, the continuous evolutionary pressure of high-speed running slowly expanded the surface area of these proto-wings until the passive lift vector eventually exceeded the physical weight of the animal, lifting it directly off the soil. However, the cursorial model immediately collided with the unforgiving laws of fluid dynamics. Computational fluid dynamic simulations proved that the drag coefficient of a running animal increases at the square of its velocity. To generate enough passive aerodynamic lift to take off from a flat surface, the theropod would have to run at speeds exceeding 50 miles per hour, a biomechanical impossibility for an animal of that mass. It would have to actively flap its wings while sprinting, But the neurological architecture required to execute a maximum output bipedal sprint while simultaneously maintaining an independent, perfectly timed, powered flapping motion with the arms is staggeringly complex. Biological systems simply do not evolve two unrelated, hyper-complex motor patterns simultaneously by accident. The resolution to this deadlock required science to stop looking at the adult forms of extinct dinosaurs and start examining the ontogenetic development of modern birds. This birthed the ontogenetic transitional wing hypothesis, which is closely tied to a bridging mechanism known as wing-assisted incline running, or WAIR. Researchers observed that juvenile ground birds, whose wings are too underdeveloped to generate upward lift, do not use their forelimbs to fly. Instead, when threatened, they run directly at vertical obstacles like sheer rock faces or tree trunks. They violently flap their half-formed wings, not to lift themselves up, but to reverse the aerodynamic vector, pushing air upward to force their bodies downward. This negative lift pins their feet against the vertical surface, exponentially increasing their mechanical traction and allowing them to run straight up a wall. This discovery seamlessly bridges the two fiercely debated models. The wings did not evolve for passive gliding, nor did they evolve to passively lift a running animal off the ground. They evolved as highly active, aerodynamic traction control systems. The feathered theropod weaponized the atmosphere to alter its own center of gravity over millions of years as the pectoral muscles hypertrophied to generate stronger negative lift for better traction. The biological engine of powered flight was silently assembled. Once the hardware was perfected, a simple rotational shift in the angle of attack converted a traction machine into a flying machine. At a planetary scale, the meaning of this scientific debate fundamentally alters our perspective on technological and evolutionary progress. When astrobiologists and physicists evaluate the Great Filter and the probability of a civilization expanding beyond its home world, the physics of the gravity well remain the ultimate barrier. The arboreal gliding model represents a passive system, efficient but ultimately a dead end, reliant on existing environmental heights and always inevitably reclaimed by planetary mass. But the cursorial, traction-based transition proves that truly conquering a new physical dimension requires the generation of overwhelming, active internal force. It demands an organism, or a civilization, to actively engineer thrust. The feathered theropods demonstrate that whether utilizing a biological wing to scale a cliff, or a chemical rocket to achieve orbital velocity, escaping a planet is never an accident of passive falling. It is the absolute triumph of directed, mechanical power against the gravity of a world. The physical architecture of the Earth is never static. It is a slow, relentless thermodynamic engine, powered by the decay of radioactive isotopes deep within the planetary core. At the dawn of the Jurassic, this planetary engine fractured the supercontinent of Pangaea, initiating the reign of the dinosaurs. But as the period drew to a close, these immense tectonic forces did not subside. They accelerated. The massive rift valley that had violently torn North America away from Africa continued to widen. Deep beneath the surface, the decompression melting of the mantle continuously extruded millions of tons of new basaltic rock, forging the massive underwater mountain range known as the Mid-Atlantic Ridge. This continuous geological expansion caused the ocean floor to physically spread, allowing the waters of the global ocean to rush in and permanently fill the void. The terrestrial bridges that had once connected the world were submerged forever. This geological severance triggered one of the most profound biological shifts in planetary history. For tens of millions of years, the Jurassic had been defined by a remarkable degree of ecological uniformity. The connected supercontinent had allowed for the existence of cosmopolitan species. The genetic blueprints of the colossal sauropods and the heavily armed theropods were distributed globally. An apex predator hunting in the floodplains of North America was fundamentally similar to a predator hunting in the river valleys of Europe or Africa. There was a continuous, unbroken flow of genetic information across the planetary landmass, maintaining a highly stable, uniform biological baseline. But as the Atlantic Ocean widened, that global genetic network was violently and permanently severed. The single, massive landmass fractured into isolated, drifting island continents. This isolation initiated the ruthless biological mechanism of divergent evolution. When a single global population is divided by an impassable geographic barrier, in this case, millions of square miles of deep ocean, the separated factions are immediately subjected to different, localized environmental pressures, shifting climates, and distinct predator-prey dynamics. Because they can no longer share genetic adaptations across the water, their evolutionary pathways irrevocably diverge. The era of the global dinosaur ended, replaced by an era of extreme, localized endemism. The separated continents effectively became massive, isolated biological laboratories, each running its own independent, high-stakes evolutionary experiment. At a planetary scale, the meaning of this tectonic fragmentation completely alters our understanding of civilizational longevity and the Fermi paradox. When astrobiologists evaluate the long-term habitability of exoplanets, a stagnant, solid crust is considered a lethal planetary flaw. A world without active plate tectonics cannot recycle its carbon, but more importantly, it cannot force biological innovation. If an environment remains stable and geographically unified forever, evolution stagnates. The species become hyper-optimized for one specific, unchanging condition, rendering the entire biosphere incredibly fragile to any sudden cosmic or geological shock. Continental drift acts as the ultimate biological pressure cooker. By constantly rearranging the geography, shifting massive ocean currents, and isolating populations, a tectonically active planet forces life to continuously solve new thermodynamic and ecological problems. This relentless geographical warfare is the fundamental prerequisite for generating a biosphere resilient enough to survive deep time and eventually produce advanced technological intelligence. The transition from the Jurassic to the Cretaceous period was not marked by a sudden apocalyptic catastrophe. There was no massive asteroid impact at this boundary, and no runaway greenhouse extinction event like the one that ended the Triassic. Instead, the boundary was defined by a slow, inexorable turning of the geological and ecological gears. As the continents drifted further apart, the global ocean currents shifted. The continuous equatorial flow of the Tethys Sea was disrupted, fundamentally altering how thermal energy was distributed from the equator to the poles. The uniform, humid greenhouse climate of the Jurassic began to fracture into more distinct, extreme seasonal zones. This slow climatic drift systematically dismantled the ecological foundation of the massive Jurassic megafauna. The vast, homogeneous forests of ancient conifers and ferns that had fueled the extreme gigantism of the sauropods began to experience localized collapses due to changing rainfall patterns and dropping temperatures. As the flora shifted, the biological machines that relied on that highly specific chemical extraction process found themselves structurally obsolete. In the northern hemisphere, the towering brachiosaurids and the whip-tailed diplodocids slowly faded from the fossil record. They were victims not of a sudden cataclysm, but of an infinitely slow, mathematically unavoidable environmental eviction. But biology abhors a vacuum, and the evolutionary hardware engineered during the Jurassic was far too efficient to be discarded. The unidirectional respiratory systems, the pneumatic honeycomb skeletons, and the warm-blooded metabolic furnaces were inherited by a new generation of highly specialized organisms perfectly adapted to the newly isolated island continents. The slow collapse of the old order cleared the ecological stage for an entirely new cast of biological architectures. This localized evolutionary pressure would soon forge the heavily armored ankylosaurs, the rapidly diversifying ceratopsians with their massive thermal frills, and the precursors to the most massive and terrifying apex predators the Earth would ever produce. The Jurassic Period was the grand evolutionary proving ground. It tested and perfected the absolute extreme limits of biological scale, thermodynamic efficiency, and mechanical design. It proved that life could not only survive a global atmospheric collapse, but could weaponize the resulting environment to build the largest terrestrial machines the universe has ever seen. As the continents completely separated and the world crossed the threshold into the Cretaceous, the dinosaurs did not simply survive the transition. They were perfectly pre-adapted to conquer a fractured, dynamic planet. The quiet, uniform global empire of the Jurassic had fallen, seamlessly giving way to the most diverse, extreme, and violent biological era in the history of the Earth.